Section 5.3, we're taking a look at polar coordinates. And I think that you'll feel like that a lot of the things that we're doing in this section look like things we've done in other areas. And so we're going to get started. We're going to look at what's called polar coordinates. We've talked a little bit about polar coordinates already. So this is a representation for a point, P, in the Cartesian coordinate system. P is r theta, where the absolute value r is the distance from the origin, and theta is the angle created by the ray OP to the positive x-axis. And a picture might be helpful, just to remind you that you really have seen this before. So if we have a point say right here in space, normally we have an xy ordered pair, right? This ordered pair is now going to be listed as r theta. The r value is this distance right here. So r is this length, and I should say the absolute value of r because it's always a positive value because we're talking about a distance. And theta is this angle measure. Have you seen that before? Yeah, right? We did this with the complex numbers, right? It looked very much like this. So this isn't new, it's just a different type of an application, or a different type of a connection to what this is doing. But the pieces are just the same. So we're going to be taking a look at finding this absolute value r value, how far it is away from the origin, and the angle measure, how far away it is from the x-axis, the positive x-axis specifically. All right, so we're going to take a couple of ordered pairs where they actually are going to give us the values, and we're just going to plot them. So we have negative 3 pi is our first one. So we're going to draw our coordinate system. Negative 3 means that I'm going 3 to the left. Okay, it's just like if it was a negative 3 for the x value. It means you're going left 3. So we're going to go over here left 3. So we're starting, if you will, right here, right? This is not where we're ending. This is where we're starting. And then it says that I'm supposed to rotate from where I am pi units. And I'm still going counterclockwise, just like I always go with trig, right? I always go counterclockwise with my angles. So where I am right now, I'm over here on what would be the negative x-axis. If I rotate around pi degrees, where am I going to end up? On the positive x-axis, right? Like this is going to put us all the way over here. So this right here, and I'll change the color, we'll make it orange, is our final point. This is the point we're plotting. So this point right here is here. Okay, this is the point negative 3 pi. You might be looking at that and saying, well, that's a really weird way to describe that point. And you would be right. There are other ways we could describe that point, and we will do so in a moment. But if it was given this point, negative 3 pi, this is the location for that ordered pair. Okay, let's try another one. So this one's giving me 6 and negative 60 degrees. So they can give me radians or degrees. We're going to be working in between those and going back and forth. But it starts out with 6. So as I'm got to have a positive 6 this time, I'm going to go to the right, instead of to the left. So I'm going to move out 6 over here. 1, 2, 3, 4, 5, and 6. So again, I'm starting, and I'll use the same yellow and orange I did before. I'm starting right here. And then I'm supposed to go negative 60 degrees. So what would negative 60 degrees look like? Okay, I'm going to go down, right? So I'm going to go clockwise because negative is a clockwise direction, okay? And how far am I going to go? 60 degrees, right? And as I move this 60 degrees, I'm not going to get all the way back to the y-axis, right? It's going to be part way there. So I'm going to get back somewhere like here. So if you want to think about drawing in kind of a ray to mark where you have come from and where you're going to, it might be helpful. I can't get it to work. Let's try again. That'll work. Here, this is the 60 degree, and it's negative, that we just went. Is that all right? Okay, so one of the things we want to be able to do is to take an ordered pair and simply plot it based on its status that it gives us the information for. The second thing we're going to do is we're going to say, okay, but there's other ways we could write those ordered pairs, maybe ways that are more intuitive, more reasonable. And the reality is there's infinitely many ways we could write that ordered pair because you know what trig does, right? You can spin around and you can spin around and you can spin around so you can consistently add or constantly add 360 or 2 pi or subtract 360 or 2 pi from any of these locations and get right back where you started with. Right? That's the cyclic nature. We talked about that when we did our trig graphs for sine and cosine, right? They keep going up and down. It repeats over and over and over again, and it never stops. The same thing happens here. I will have infinitely many ordered pairs that will have this same location in space. So I'm going to take my graphs, and I'm going to pull them over here. I don't need that orange piece that I did above. And I'm just going to put it right over here to remind ourselves visually where we are. So there's a very nice way that we could have written this point instead. What would be the most intuitive way to write that orange point? This seems the most natural. 3 and 0. Positive 3 on the x-axis, right? You go out from the origin 3, and you simply don't make any angle movement at all. We were in radians, so I'll leave it in radians and call it 0. If it helps you, you're welcome to write radians here to remind yourself we're not talking about an xy pair. This is an r theta pair. So you don't have to have the word radians, but if it helps you to see that, you certainly could. Okay, so this would be another way to write this. But let's think again, what else could we have? Well, I could still do 3, but instead of going 0, what could I do? 360, or in radians, it would be 2 pi. So I could take where I am here, and I could go all the way around one time, and I would be back where I started with, right? Okay, so we could have a 2 pi here. I mean, but that's not all I could do. I could go the other direction, right? I could have a negative 2 pi, and that would work too, right? Yeah. Now those are all the ones, I mean, I can keep going. I can keep going 4 pi and 6 pi and 8 pi and negative 4 pi and negative 6. I could keep doing this, right? Yeah. Could I do other things instead of positive 3? Like, are there other options with negative 3? So if I went negative 3, like I did to start with, and I was given to go pi, so I went down like this, right? What else could I have done and still arrived at the same location by starting over here at negative 3? I could have done negative pi. Any other thoughts? I could do 3 pi. Let's do one more just for fun. Your pick. What could we do? Negative 3 and what? Negative 3 pi. We could do 5 pi or negative 5 pi, right? We have these same possibilities over and over and over again going around and around. Does that make sense? So the way that these questions look like inside of the book when I'm looking at them is they say something like, it's like a multiple choice kind of thing. They give you an ordered pair and they ask you which of these 4 options are the same location. And so you have to be able to identify, oh, this one works and this one doesn't. Does that make sense? So you may have one of those places where they say, select all that apply. I hate those multiple choice questions, by the way. I'm not going to ask a multiple choice question. If I'm going to ask you the question, it would be more like this. Find me 2 more points that work. That's how it would be if I phrased it. But they don't have the capability inside of the program to make that work as well. And so they're going to do it probably as a multiple choice kind of question for you, okay? Okay, let's try the same other point, or this other point that we had. Let me get my graph in there. All right, so I went out to 6. Let's start with positive 6. What other angles could I do if I went positive 6? So if I go negative 60, I'm down here. What if I go positive? How far would I have to go if I was going positive? What is it? 300. Okay, so Melody, how did we get 300? Yeah, so it's 360, right? So if I take my negative 60 location, because that's where I am, and I add 360 to that, I'm at 300. Does that make sense? Okay, so can we do another one that's a positive 6? In some ways, radians are easier to work with, but... Okay, so 660. So I'm at 300, and if I add another 360 to it, I'm at 660, right? Because I can keep doing this. What if I wanted a negative 1? Okay, and Carson, how'd you get 420?
Just 60 plus 360 is
yeah.
negative.
Yeah, so we've got negative 60, and then we would subtract 360. So negative 60 and negative 360 would be negative 420. Okay, so this 420 right here is probably our least natural one to do. I get that. But it's negative 60 minus 360. Okay, does that make sense? Okay, this sort of idea of continually adding 360 or continually subtracting 360. Okay, but we don't have to have a positive 6. We can also start with negative 6. If I went negative 6, that would actually mean that I would have gone this direction first. So if I'm over here on the left-hand side of the graph at negative 6, let me mark it on here in case somebody's looking at this later. If I'm over here, how would I get to here?
120.
Was it?
120.
It's 120. Why is it 120? How'd you get that? Because this is not just to add 360 bit at this point, right? Yeah, so if you have 120 and add 60 more to it, you're going to be at 180, right? So this whole bottom half would be a 180. So yeah, it's 120. What else could I do at negative 6? We're going to fill in a couple more. I just want you to see options because I don't know how the multiple choices are going to look. So I want you to feel comfortable, with seeing lots of options. What else could I do if I did negative 6? Okay, so I could go the other direction, right? So if I went the other direction from negative 6 and I come around here, where am I going to be? It's not negative 300. What is it? So it'd be this amount. What's the top part? It's 180, right? Plus 60 more. So what's 180 and 60 more? 240. I would be at 240, and it would be negative 240 because I'd be going around clockwise, right? So if I started at negative 6 and I go half of the rotation, I'm at 180 and 60 more. That gives me 240. Okay, let's try one more. You can go either direction. Let's do a negative 6 still. So we're down over here at negative 6. How do I get to this point? Using, if you will, either of these locations are fine. I've got a 120 and I've got a negative 240. What could I do to get another one? Just add or subtract 360, right? So let's take the first one. So if I took 120 and I added 360, what am I going to get? I'm going to get 480, and that would be another location. And we could literally do this, forever, right? Like this is an infinite process. We could do this over and over and over again. So pay special attention when they're looking at those options of which ones do and which ones don't have the same properties. Okay. So we're going to talk then about how we go back and forth between polar coordinates and rectangular coordinates. And these are all things we've done and seen before. In fact, I'm going to copy this picture, and we're going to start from this picture on our discussion over here. So we have the same picture, and we've talked about this point at the top. I'm going to write it in yellow as well, being the ordered pair XY. And it's also the ordered pair r theta, right? So the x and the y come from the fact that if I dropped this down here and I dropped this over here, I'd be creating a triangle. We've worked a little bit with triangles this year. This side of the triangle is the x value, and this side is the y value, which yields me the ordered pair xy. Shake your head if this picture looks familiar. Like I think we did it a week ago. We did it a week ago with a different context, but we did this same picture a week ago. And we established several different equation relationships here. For example, looking at this from the standpoint of like SOHCAHTOA, here's my angle theta here in the middle, right? So this angle theta, if I look at the adjacent over the hypotenuse. What is adjacent over hypotenuse? What trig function is that? That's cosine. So there is a cosine function, cosine of theta, that is adjacent, which is the x value, over the hypotenuse, and that is the r value. And you will notice that we drop in these definitions the absolute value because r is going to always be positive for what we're working with in terms of the conversions. Okay, so if you want to write the absolute value in, feel free. But if you look at anything related to this in any other resource, they're not going to have them there. And I'd like for us to change this into a form that solves this for x. In other words, if I multiply r to the other side, I will get that x is equal to r cosine of theta. Right? Is that okay? Okay, we can do the same thing with the hypotenuse and the opposite side. So what trig function relates the hypotenuse and the opposite side? That's sine. So this is sine theta is y over r. And if I solve this, I would get, for y, I would get y equals r sine of theta. So it's these ones over here on the right that are going to be my helpful places to look for converting in a minute, which is why I'm writing them that way. There's a couple other things that are helpful, though. If I don't want to relate the r value to anything, but I instead want to relate x and y to one another, what trig function will relate the x and the y in this triangle? Tangent will. So this is that the tangent of theta is equal to y over x, right? And why is this helpful? Well, it's helpful because I can solve this for theta by doing the inverse tangent, which we've been doing at different points along the way as well, right? So again, this version right here allows me to find theta. So the top equation allows me to find x if I know r and theta. The second equation allows me to find y if I know r and theta. The third equation allows me to find theta if I know x and y. What is an equation that's going to relate x and y to r? Look at where they are. What's going to relate x and y to r from a picture? X, y, and r. How are they related in my picture?
Oh, absolutely.
Pythagorean theorem. Yeah, they're Pythagorean theorem, right? So I have that x squared plus y squared is equal to r squared. And if we take the square root, we're going to get an absolute value going on with that, right? So r is going to equal potentially plus or minus. That's why we're going to be able to have positives and negatives of x squared plus y squared. I will say that the version that we tend to go with is actually this version, not the other version, and then we simplify from there. So these ones that are in yellow are the ones that we're going to kind of gravitate towards as we're making conversions. And it seems unnecessary for us to change the ordered pair points that we've been working with, so we're going to keep them. Okay? So we have the same 2 points showing up again. Negative 3 pi and 6 negative 60. Okay? So we're going to be asked here to find the rectangular coordinates. In other words, what is x and what is y? So whenever it asks you, I didn't get the directions changed. I checked those too. I didn't get that here. So I think they're right on your paper if you've printed them out. The polar coordinates above are given. Find rectangular coordinates. So we're going to find those. So this phrase, rectangular coordinates, means that we're going to find x, y. Okay, so jot that down for yourself. Anytime you see the phrase rectangular coordinates, they're talking about x, y. Polar coordinates is talking about r theta. Okay, so we have 2 equations that find for us x and y. X is found by doing r cosine of theta, and y is found by doing r sine of theta. So then, what is r? Negative 3. So we'll do x first. Negative 3. What is theta? Pi. Okay, so now we have to think unit circle. These are going to be unit circle values. It keeps coming back over and over and over again. What is cosine at pi? It's negative 1. It's negative 1. Unit circle, right? So over here at pi, our cosine value, our x value, right, on the location is negative 1. So this is x is equal to negative 3 times negative 1. What's that give me? 3. Okay, let's do it for y. So y is equal to r, which is negative 3. Sine of theta. What is the sine of theta? I'm sorry, the sine at pi. Sorry, get my pi in there. What is it? It's 0. And negative 3 times 0 is 0. So the ordered pair that I get here is 3, 0. And remember, this is x, y. Now, look at my picture. It's the orange dot, right? Is that orange dot the ordered pair 3, 0? Yeah. So your graph should, it should correspond to what you just found. There shouldn't be a disconnect. If there's a disconnect, it's probably an error. Maybe there was an error when you made your graph, or maybe there was an error when you did a calculation. Maybe you missed a negative sign, or maybe you were thinking sine instead of cosine. Stop. Ask yourself, does this make sense? If it doesn't make sense, there is an error, and you should figure out where it is so that you can fix it. Okay, let's try the other one. It's a little bit more interesting because it's not at a quadrantal angle. It's not on one of our axes. It's at negative 60. So we have x equals r cosine of theta. My r now is 6, and my theta in degrees this time is negative 60 degrees. So in the unit circle world, right, this is where we are down here. I'm going to copy this over to our other screen. I don't need the orange part, so I won't copy that part. All right, I need to know what this ordered pair is, right? That's how I'm going to find my x and my y. What is the ordered pair? Like, this is not the ordered pair for negative 6, whatever. I just want to know for the 60 degrees. This is from the unit circle. Okay, so I'm from the perspective of the unit circle. What is it? Okay, and are there any negatives involved? Yeah, the negative here, right? Okay, so we've got 1/2. My x value is 1/2. And I don't need these here. Let me erase them. Okay, so this is not a measure of 6 out. This is just a unit circle value. I don't want you to misconstrue what I'm saying because picture-wise it didn't look right, right? Didn't look like it was 1/2. Okay, so I'm at 1/2. And then the other or corresponding unit on the unit circle is a negative square root 3/2. Which of these is the cosine value? The 1/2. Okay, so over here I now have 6. I have a 1/2. And what is 6 times 1/2? 3. Let's do y. Y is r sine of theta. R is 6. Theta is negative 60. What is my y value? Well, it's the other one, right? The negative square root 3/2. So for my y value, I have still 6 here at the beginning, and then I have negative square root 3/2. And what does this simplify to right here? Right. Now, it's a little bit more difficult. I don't mean to box it in, I'm sorry. It's a little bit more difficult to verify this visually, that ordered pair, when I did actually have the locations was correct, right? Like this should be the XY ordered pair now, 3 and negative 3 square root 3. Like that's what I have. But we should be able to see if it seems realistic. Make sense? So if I put my values back in now, where I can actually see that this is out here at 6, and I go down here, 2. And my scale is probably not quite right. I get that. But we're just looking for believability in what we're doing. Like, does it seem reasonable? Does it look like I'm about at 3 on the x value? That seems about right. And if I multiply, is the y value negative? Well, definitely my y value is negative down here, so at least that part's right. And if I multiply 3 times the square root of 3, is it something in between 3 and 6? It will be. So this is a reasonable value for us to be getting. We can feel pretty comfortable that we're not making any blatant errors in what's going on. Okay, so this is moving from polar coordinates into rectangular coordinates. But we want to go the other way as well. We want to be able to start with a rectangular coordinate and turn it into polar. So that's our next one. There's only one of these examples because I've asked for us to do this in radians. We'll do it in degrees too, just so that you can see that in case there was a question that asked you to do it in degrees. But there's not a lot different in terms of those processes. It's just a conversion between radians and degrees, which we've been doing all semester. So we have the ordered pair negative 3, 3. And if it helps you to start with a picture, and in fact, I would encourage you to do this. I keep telling my kids at home all the time, if you just draw a picture, it would save you a lot of time later in knowing if you've got things that make sense. They don't believe me. They still won't draw pictures, and they still keep making mistakes that their pictures would help them to not make. So I'm going to encourage you to same. I would draw a picture. This is the value negative 3, 3. Is that all right? Okay. So I need to find the r theta value. So from this picture, that didn't look good. Let's try again. We'll do it in yellow. R value is the distance back to the origin. So this is r. And the theta value is this angle measure right here. Does that make sense? So just looking at the picture, you should know some things, right? You should know that if you find an angle measure that's sort of reasonable, you're going from left to right, it's going to be a positive angle. If you're thinking in terms of radians, it's between pi halves and pi, right? If you're thinking in terms of degrees, it's between 90 and 180. It gives you a lot to go off of just by looking at the picture and what you guys know about angles. So that's a helpful piece of information. The other thing that it should tell you is that your angle started out over here at 3, right? I mean, like we were over, I'm sorry, I didn't say that right. Our values for x and y are at 3. So this is at -3 out here. Let me do it in white. And this is at +3 up here, right? So this measures 3 and this measures 3. And so this length that I've got right here along the R, it's going to be more than 3. Because straight to the left was 3, straight up was 3. If I go at an angle, I've gone further. So my number needs to be greater than 3. All right, now in terms of actual computation, we can find r and theta using, where did it go? Was it that? I passed it, this one. Using these bottom values. Theta can be found by doing tangent stuff, right? And r can be found by using the Pythagorean theorem. So we're going to use those. So even if you don't remember the formula that I had boxed in sort of in yellow on the tangent one, we should be able to look at this picture and we should be able to create a triangle and say, hey, look, here is a triangle. And in a triangle, I know some things. Right triangle, I know the Pythagorean theorem. So in the Pythagorean theorem part of the triangle, I know that x squared plus y squared is equal to r squared. And with Pythagorean theorem as well, opposites and hypotenuse and all these kinds of things, I know that the tangent value is y over x. You don't have to memorize these things. You've already done that. You know them. So let's figure out what they are. Well, my x value is -3. My y value is +3. So what happens when I get -3 and square it? I get a +9. And then +3 squared is 9 as well. I add those together and what do I get? 18. What will I do to find r? Square root. And we do have to simplify square root of 18 because it does simplify. How will 18 break down? 9 and 2. You can either then look at this and say, well, I know what the square root of 9 is and move forward. Or you can break the 9 down further and say, hey, look, there's a 3 and a 3. I'm looking for doubles. Once I see the double factors, that number comes out. So this over here is actually 3 square root 2. Now, that's not exactly true. Does anybody see the assumption that I made that was a little bit of an assumption of a leap? It's a positive or a negative. Now, we only have to find one ordered pair, so we can do this and ignore the negative. But in a moment, I'm going to show you that there's another way we could do this because we've done this already, right? Like these have multiple representations. One of them is going to be 3 square root 2. But we'll also find a negative one just so that you can see that there is a negative one as well, okay? So we'll find another option so you can see those two, both those things. So we're going to look then for theta. That's the other piece we have to do, right? Okay, so tangent of theta is y, which is 3, over x, which is -3. This gives me a tangent value that's -1. Now, that's not especially friendly because it's harder for us to think about tangent values on a unit circle than it is in sines and cosines. But the tangent value of 1's not bad. Tangent value of 1's or -1's always happen at what kinds of angles? 45s, right? So if you're thinking radians, we can do that too, but degrees, it's 45s. So what's the 45-degree angle in quadrant 2? What is it? 135, you got it. It is 135, okay? So you've got 45, you've got 135, 225, and then, what's the other one? 315, yeah. Okay, so it's 135 in this angle, or in this quadrant. So this theta angle is 135. The directions actually told us to do this in radians, though. So what is this in radians? It is 3 pi over 4. Okay, so this is why I didn't do 2 questions, is because the only difference between me asking about it in radians or degrees is the radian or degree measure that you memorized from the unit circle. So down here, if I have 3 square root 2, this is 3 pi over 4. Now, let's think for a second. If I had -3 square root of 2, what is an angle that I could use instead?
It'd be 45-degree angle on quadrant 3, right?
Well, so let's think our picture. So let me sketch a new picture so that we can put it there. I'm over here if I'm at negative 3 squared 2. How do I get back to up here? How do I get here? It's still a 45-degree angle, right? Close, but it's negative. It's a negative 45-degree angle. So this would act, because I'm going the wrong, quote unquote, I'm going clockwise, right? So this is a negative 45-degree angle, or negative pi over 4. I know that feels a little weird, but that would be another answer that is correct for this problem. And again, if it's one of those ones where they're saying choose all of the answers that are correct, that'd be one of them. Okay? All right, a couple more things. We're going to actually take equations now and change them around. We use the same formulas. There's nothing about this that's different. We're just not going to have an ordered pair at the end. Our answer at the end will look different. So this one says convert each rectangular equation into a polar equation that expresses r in terms of theta. This phrase right here means that we're going to solve for r at the end. That's what that phrase means. Okay, so we're going to turn everything into r's and thetas and then solve for r. All right, so taking a look over here, we've got y squared equals 2x. What can I replace the y with in this equation? What is y? We used it over here. What is y? Y is r sine theta, right? Now, I know we have a y squared in a formula as well. It's like right here. But it's not helpful because it still has an x in it. Y'all with me? Having x in that formula is not a helpful way for us to convert this. I'm trying to get the x's and the y's to go away. So I don't want to replace y with something that's got x in it. That's not a helpful move. But this one works just fine to change the y into r sine of theta. And that whole thing is squared because it says that y, which is r sine of theta now, is squared. What about x? What is x? Yeah, r cosine of theta. Now, in terms of the first half of this question, get rid of the x's and y's and make them r's and thetas, we've done that. The only thing we haven't done is solve this for r. That's not that bad. So here's what we're going to do. Notice, we'll square this first. This is r squared sine squared of theta equals 2r cosine of theta. Tell me something you might want to try. What looks like a reasonable thing to do? We wanted to say r equals on the left. We'll go with the left. What's over here with r that might want to move? Sine squared. We're going to move that. We're going to move it with division, right, because it's multiplied. Now that's almost got r by itself. What else might we want to do to get r by itself? Because there's actually a really nice step that's not something we normally do, but we can do it here. What do you have an idea of? We could square root. Square root's going to make things kind of look ugly, so there's actually a nicer option here. We can divide by r. And the reason that dividing by r is nice is because it's going to cancel here. Y'all see that? That's a little friendly on this one. That doesn't always happen. Square roots are certainly a possibility of things that we could have to do. It's just that on this one, it divides out nicely. All right, so on the left-hand side, I now just have r. And on the right-hand side, I have 2. And I have cosine of theta over sine squared of theta. So we would kind of like to clean it up somehow. Doing 1 minus cosine squared might not be the most helpful way to clean it up because then I have subtraction in a denominator. But is there any way that that denominator can come up to the numerator? What would it be? What is division by sine the same as? This is one of the trigonometries you have to memorize that I won't give you. Cosecant, yeah. So sine and cosecant are reciprocal identities. So if sine is in the bottom, that's the same thing as having cosecant in the top. So it would look like that. Okay, so this is a perfectly reasonable way to leave this. 2 cosine of theta cosecant squared of theta. I do want to show you one other way of this that does clean it up a little bit. I'm okay with it like this. I'm not telling you you have to do my next step, but I do want you to recognize that there is one more thing, especially if you look at one of those like, help me solve this inside of my math lab and it does something, you're like, whoa, what did it just do? Right? Like that shouldn't be a place where you're just surprised. So I want you to see it here and first, okay? Instead of writing this way, another option would be to write this. So let me do this over here in a different color so you can see it's an optional thing. So we have 2 cosine of theta. And cosecant is the same. Oh, sorry. Let me write this again where we had it as sines. Yeah, let's do this. I'll write it this way. Right? That's the same thing as sine squared, right? And if I grouped these together instead, what is cosine over sine? Yeah. So this, if I think about it as cosine of theta over sine of theta, and then I have the 1 over sine theta over here. This first one is cotangent, and the second one would be the cosecant. And so is that more reduced? It is, because there's no squareds. I don't find that to be a particularly like, you got to be able to simplify it to that form kind of thing. But I want you to see that you can. Is that all right? We're just getting rid of the squaring because there is a way to reduce the cosine with the cosecant slightly, or the sine squared slightly. Okay, last question. We're going to take the polar equation and turn it back into rectangular form, and then we're going to graph it. Now notice what we're not going to do. We're not being asked to graph this equation in polar form. Okay. If you have a TI-84, your calculator will do that, by the way. It will. You can come see me. We can chat about it. That's fine. But not everybody has one, and we don't need one for doing this. That's not what the question's asking. But it wants us to turn it into rectangular form first. So rectangular form means I want to have x's and y's when I'm done. So yeah, we're going to manipulate with this. So the first thing I'd like for us to do is to rewrite this with cosine in it, because cosine is friendlier, because our formulas involve cosine and they don't involve secant. So how could I rewrite secant so that it's not written as secant, but it has cosine in it? How are secant and cosine related? They're reciprocals as well. So if there's a secant up in the numerator, I could put a cosine in a denominator, right? So we're using the fact that secant of theta is 1 over cosine of theta. So I'm going to rewrite this as 6 over the cosine of theta. Okay. Why am I going to do that? Well, because I want cosines involved because my formulas involve cosines. I want sines involved. I want tangents involved. Those are the 3 I want because my formulas use those. But this is kind of a cool trick. Check it out. This cosine of theta, if I multiply it to the other side, what will I have? R cosine theta. And why in the world is that friendly? Because it's the same thing as x. This is just the equation x equals 6. Now we're going to lean in on a little bit of your algebra skills. Do you know what the graph of x equals 6 looks like? What is it? Okay, so the 6 is on the x value, right? So this 1, 2, 3, 4, 5, 6. This is x equal to 6. But it's not just that point. It's a line. What kind of line? It's vertical. Everywhere along this line, the x value is 6. Right? This is the line x equals 6. Your calculator won't graph this, by the way, because it's not a function. Your calculator will only graph y equals functions, and this is an x equals equation. So you can't just plug this particular one into your calculator. This is the equation x equals 6. And if we were in polar form and we graphed 6 secant theta, it would give us this same graph. But that's a lot less intuitive to know than to know what the graph of x equals 6 looks like. Any questions? All right.